So last meeting, we have started with the discussion. I gave you an introduction on properties of solutions, and we discussed what are solutions. So when we speak of solutions, they're referring to homogeneous mixture of what we call a solute and a solvent. And discussed as well that when we speak of the solute, it's the component in your mixture that is present in the least amount. So the solvent is said to dissolve this small amount of solute. We also discussed that we don't limit only our examples of solutions to liquid solutions. So we can also have gas solutions, which is commonly given as an example, the air. And then we also have solid solutions, wherein we have the mixture of different metals. Now, we also covered as an example what happens when sodium chloride dissolves in water. So there's a need for your sodium chloride, known as your table salt, to first dissociate into its component ions, the sodium and the chlorine ions. That way, they can be solvated. The term is solvated by water. So in the case of the solution process, when your solvent is water, another name for the process of dissolution is hydration. So we say that when your dissociated ions of sodium and chlorine already get separated from each other, the said ions are being hydrated by water. That is, if water is your solvent. Okay, so this is what is happening. You have the green and the purple, or is it bluish purple balls representing your sodium chloride molecules, and you have here water molecule having 2 atoms of hydrogen and an atom of oxygen. So prior to the dissolution process, your sodium chloride atoms or ions need to be separated from each other. That way it can get solvated or hydrated specifically by water, which is in our case here the solvent. Okay, this we have covered, and I'm just reviewing here, and this is what actually happens to your sodium cation and your chlorine anion when it's being surrounded by, hydrated or solvated by water molecules. So your sodium, being a positive cation, gets attached to the oxygen in your water molecule because oxygen is negative. And your chlorine anion, so it's negatively charged, get attached to your hydrogen in your water molecule because hydrogen is positively charged. So this is what is happening when your sodium chloride gets dissolved in water. Now, in the process of solution, there are 3 steps in the, or shall I say, there are 3 specific energy steps in the formation of this solution. So in the separation of solute molecules, you have this energy delta H1. And in the separation of solvent molecules, we have this energy delta H2. Now, once they are separated, we have the formation of the solute-solvent interaction, and there's also energy associated with this. Now, we need to sum up all these energies, all these delta T's, or the changes in the enthalpy, and that would then define the enthalpy of the solution, or the delta H of the solution. It can either be positive or negative depending on the existing depending on the intermolecular forces that is happening during the process of dissolution. And then in the separation of your sodium and chlorine ions for your sodium chloride, and in the separation of your solvent molecules, you have this delta H1 and delta H2 associated with it. And once they are separated, only then can they interact with one another. So this refers to the ions of your solute and the water molecules. So now they can interact with one another. There will be no interaction unless these ions in your solute gets dissociated from one another, and your molecules in your water get separated as well from each other. Now, since the breaking of attractive forces requires energy, so what attractive forces we need to break down? The forces that attracts sodium and chlorine ions, that way they get to be attached to each other. So it needs to be broken. This particular attractive intermolecular forces that needs to be broken requires energy. And as such, the process is endothermic, meaning energy is needed. Whereas when we form attractive intermolecular forces now between the dissociated ions of your solute with your water molecules, that's the time that we have exothermic interaction, or shall we say exothermic uh, shall we say manner of or usage of energy. So in this case, class exothermic, meaning energy is being released. Okay, this one in endothermic, energy is needed or it's being absorbed. Now, to determine whether your delta H solution is positive or negative, we consider the strengths of all your solute-solute and solute-solvent interaction. So since delta H1 and delta H2 are needed, so it's positive, whereas delta H3 is the energy that is being released, so it is negative. So it's possible to have either a delta H3 which is bigger than the sum of delta H1 and delta H2, which will result to a negative delta H in solution. Now, if delta H3 is less than the sum of delta H1 and delta H2, then you will have a delta H of solution which is positive. It's as simple as that. Okay, so in the case of sodium hydroxide being added to water, so the solution of sodium hydroxide in water, the delta H of your solution is negative 44.48 kilojoule per mole. So you see this negative, meaning the released energy is greater than the energy that was needed to separate your sodium, your oxygen, and your sodium rather, and your hydroxide and ion from each other in your sodium hydroxide compound. So this being negative, so tells you that energy is being released. Now, if energy is being released, if you're performing this experiment in the lab, what will your observation be? If energy is being released or if sodium hydroxide is being dissolved in water. If you have done this before, or even if you haven't done this, if you have a negative delta H, what do you think will be the thing that you will observe when you conduct this experiment or when you do this dissolution process? What do you think is expected to happen if you haven't done this? Or if you have done this, what have you observed? Dissolving sodium hydroxide in water. No one has an idea? You haven't performed an experiment where sodium hydroxide pellets or shall I say parang daw chip siya being dissolved in water? You haven't done this? So let's say, for example, everybody is silent. So you haven't done this. You don't know what's going to happen when sodium hydroxide is released or placed in water and dissolved. But with this negative amount of delta H solution, what do you think will you be able to observe? Or what do you think will happen based on this negative value of delta H? Okay. Yeah, it will separate because we are talking about the solution. If there's no separation, you won't have one homogeneous solution. So what I mean is, what do you think will you be observing? Like what do you think using your senses will you be able to observe based on this negative 44.48 kilojoule per mole delta H of solution? No chemistry teacher informed you what will happen if you have an endothermic reaction or an exothermic reaction? Kyle Angulo, very good. So heat would be produced. If heat will be produced, very good, Kyle. If heat is produced during the process of the dissolution of sodium hydroxide in water, when you're going to dissolve, for example, sodium hydroxide pellets in water placed inside the beaker class, normally we instruct our students to have it placed over a water bath. Meaning you place your beaker inside a water bath. I think everybody knows what a water bath is. Why? Because over time, as your sodium hydroxide gets dissolved, the water inside the beaker becomes hotter and hotter. The more solids you have there, the greater is the released energy. And this is exothermic, very, very hot. So if you will get burned if you were hold the beaker that holds the solution. So that is why the process is and that is why we place rather the beaker in a water bath. Because if you don't place it in a water bath class with continuous flow of water, there will come a point that no sodium hydroxide pellets will get dissolved already because your water is too hot already inside the beaker. There is release of energy, and as such, of course, you expect that the solution produced will be very hot. Okay, so that's the question, that's the answer that I'm trying to get from you. What will be observable in terms of your senses when you dissolve sodium hydroxide in water, knowing that you have delta H of solution, which is negative. So delta H is a representation of the heat that is being released. In this case, class, it's released heat because it's negative, meaning exo. If this is positive, your reaction would need a certain amount of energy for it to be for it to proceed. Okay, so in this case, it's negative. So the container will feel warm. In the case of sodium the sodium nitrate, if you add water to it, contrary to the example of the sodium hydroxide, this time your solution will have a positive delta H of solution. So instead of it getting warm, when it's releasing energy, this time your solution will be, if not colder than the usual room temperature, it will be cold. It will be just the normal room temperature because there's no released energy. If there's no released energy, then we won't have a hotter environment produced. Okay? Or we will not have an environment of this sodium nitrate and water which is warm, meaning they don't release energy when they react with one another in the process of the solution. Okay? Now, this is mentioned in chemistry always. I remember this being discussed in my chemistry in high school. The rule is your polar solvents dissolve polar solutes. Non-polar solvents dissolve non-polar solutes. As such, we have this old saying, like dissolves like. So if your solute is polar, then your solvent has to be polar. When your solute is non-polar, your solvent has to be non-polar as well. If they're not the same in polarity, there will be no dissolution that will occur. Okay? Now, if delta H of solution is too endothermic, a solution will not form. Meaning, going back to the example of the sodium hydroxide solution that I mentioned a while ago, if there comes a point, class, that when you try to dissolve sodium hydroxide in water, and it will not get dissolved anymore, meaning the reaction is too endothermic already. Meaning, init-init na siya nga hindi na siya ka-dissolve pa sang sodium hydroxide nga ibutang mo kag i-dissolve. So the only way that you can have it dissolve is you add more solvent, or instead of just using normal tap water in dissolve it in the water bath. So meaning the water in the bath gets to be replaced continuously. That way it will not also boil, or it will not be turn to it will not get hot and hotter over time. So then that particular water in the water bath has to be colder than normal room temperature. Okay, that way, your sodium hydroxide gets to be dissolved. So that's in the case if your delta H of solution is 2 endothermic, meaning negative siya nga dako-dako. Okay, meaning it's 2 endothermic. It releases a lot of energy. Now, feel free to interrupt. Use your, okay, there was a question. Is it okay to do ice bath instead of cold water bath, Miss? I suggest that you don't use ice bath, but rather use water at a temperature that is lesser than the room temperature. If it's ice bath, my worry is your beaker is very, very hot and your water is very cold if you're going to place hot. So what will happen to your beaker? So over time, it will get cracked because of the large difference in temperature between the solution in your beaker and that in the water bath. When we do water bath class, it's not cold water actually that we're using. It's just normal room temperature water. But if let's say the environment is too humid or taas ang temperature, it would be better if the water that you'll be using is something that has already stayed overnight and it's colder than the one that is being dispensed by the faucet or kung diin ang source ng imo nga water nga gasulod sa bath. Kaya normally in the laboratory, the water that we're using in our water bath, even if it's a continuously flowing water, it's just water from the faucet. So kung ang, for example, in the case of a particular school that uses a, shall I say, a water tank that recycles water, let's say rainwater. So it's okay lang kung ang water tank is concrete, the water inside it will be, shall I say, a little bit tapered in temperature compared to the water that will be dispensed by Basiwa or by our source, Basiwa water. Okay, if not, especially if pipeline is exposed to sunlight or init ang lugar where the pipe is being transported, where the pipe that transport your water is situated, then init ang tubig nga nagasulod man mismo. To paano mo mapakold ang imo nga solusyon nga may sodium hydroxide kung ang water nga ginagamit mo magpakold sa iya, init na nga daan. In our case here, diri sa Aeroreco, the thing is, basta init na gani ang temperature, we don't have a steady supply of Basiwa water, so we have water tanks. So over time, basta init-init, kung summer, init man namon tubig. It's just like you have normal heater without having a heater at home. It's because naka-expose ang water tank sa sun, so init siya. So that's what I meant with I say na dapat ang aton water tani room temperature lang, especially if not nga hindi collected water from a source. Okay, so hindi wala gagamit ice cold water in the water bath. It's just normal room temperature water. We don't also want to have this what we call you will encounter this in your material science. The process of, I'm not sure if that term is right that I'm going to use. If my memory serves me right, in tempering bala from very hot to very cold. So amo nang matabo. Kung init-init sang solution mo sa sulod, so ibutang mo sa tugnaw, there might be something that will happen to your container. Ti aton container, beaker lang man. So although ang aina nga mga beaker nga ginagamit sa lab can withstand temperature. Pero I'm not certain if it can withstand temperature nga init-init, tason cold, ibutang mo siya sa cold, makrack siya. As per my experience, when I did my own experiment, that was 9 years ago when I did my own experiment for my dissertation, my Soxlet extraction equipment, even I forgot the name, got cracked over time, long use of long heating procedures, and then cooling it down. I don't even place it in water. I just simply let it cool down room temperature, nag-crack pa gani gihapon. So glass can withstand a certain temperature range, but prolonged use at high elevated temperatures will sometimes or most of the time take a toll on your glass rather, and will crack. Okay, now we go to spontaneity. Spontaneity, how spontaneous is something? When you speak of spontaneous, like say if a person is being asked a personal question and that person answers right away, that's a spontaneous answer. Something that is not really thought of and given much thought of. You are asked, how old are you? And if you don't, it doesn't matter to you to tell to the person how old are you, then you will give a spontaneous answer. Like, I'm 50 years old, or I'm 60 years old, or something like that. But there are people who will think, what would I do? Will I tell this person my real age, or I will not? So that's not something spontaneous. You thought of it first before you give out the answer. Okay, so in here, we can also apply the same thing with solution formation, spontaneity, and the degree of disorder. When you speak of a spontaneous process, it occurs without outside intervention. Something that is expected, so something that is spontaneous. Can you give me an example of a spontaneous process? It does not require any outside intervention. Observable, spontaneous process that you can think that does not require any outside intervention. You may write your name, your answer on the chat box. Have you observed any natural occurring process that does not require any outside intervention? It will simply happen. And what's that? Wala, Geb. Like mo may dumduman nga natural occurring phenomena that is spontaneous, that whether you like it or not, it will happen.
Ulan, init, miss.
Ulan, init. Ulan, init. Ano pa de? Melting of ice. Correct. Even if your ice is, if your ice is placed in a room, normal room temperature, it will melt. Boiling of water. Boiling of water is not spontaneous. You need to expose it into a very high temperature, a very hot source rather, for it to boil. So it's not spontaneous. Melting of ice is, because once you take out your ice from the refrigerator, freezer, that is, and you, even in just on the fridge, yung kuha mo sa freezer, yung transfer mo sa fridge, there will be some degree of melting. Okay, some degree of melting because the temperature in the fridge is not the same as that in the freezer. We know that for water to be kept solid, that is ice, it has to be 0 degrees. So for example, your freezer is at -19. Your fridge is at 20. Yes, 20 degrees Celsius. Something wrong with your fridge probably. Just like what happened to ours here. Say -19 ang freezer, ang fridge at 20. So there's something wrong with the other side, but the other side is okay. So what will happen to your ice? It will really have some degree of melting because its temperature is not anymore 0. So your water is expected to melt at that. So melting is a natural occurring process. Thank you. Very good for the example of the rusting of iron. It's a spontaneous process. You place iron outside, let rain or shine, it's there. It will, of course, rust. So very good. Cooling of hot coffee at room temperature. Pwede. So mag-cool down ang water, ang coffee in room temperature. Flowing of water. What do you mean with flowing of water? Water will not flow unless you, water that is contained or water that is in a body of water. What do you mean by this example? So water will not flow if it's placed inside a container. So nothing will happen to it. It will stay inside the container. Flowing of water, if you say flowing of water, where? Decay of fruits, very, very good example. The decay of fruits or the decomposition of living things. Okay. All living things, when they die, when they expire, decays. So it's a natural process. It's a spontaneous process. Sweating of the hands. Not everybody has sweating of the hands here, but there are people who have sweating hands, so something spontaneous. But there's some disorder associated with this on sweating of the hands. They say I do have sweating of the hands also when I was young, but as I get older, I don't have it. I don't experience it anymore. Even when I sit down, when I on the chair, there will be some degree of moisture on where I sit on. So, but there's something wrong though with our digestive system. But I let it be. When I got old at this age, I don't experience it anymore. Flowing of water downhill. Okay. By virtue of gravity, not only water, anything will flow downward if you place it on an elevated location. Let it be, then it will flow downward by virtue of the action of gravity. Okay? Decay of fruits. What else? Evaporation of liquid that is inside an aquatic flower pot in a summer season. Or shall we say evaporation per se? It's a naturally occurring process. Water evaporates from oceans, from lakes, from rivers, and even water that are being stored in containers. They do evaporate. Okay, so not necessarily that they will be placed in, although this one is a specific example, but evaporation is a spontaneous process. Okay, so you know what spontaneous is? Something that does not require any outside intervention. It will happen. Okay, now we get old, so it's a spontaneous process. No matter how those anti-aging pills are that are being sold online, say you will grow old in, shall I say, in a slower rate, slower pace. If you drink this, your skin will be better, but eventually you'll still have the signs of aging. Everybody gets old. Okay? Wala sang may shall I say, term natin, wala sang may gabato sa kalibutan. So all of us gets old. Okay? Now, we continue with what we're talking. So when energy of the system decreases, so let's go back to our system. Example, the dropping of a book. So if you're carrying a book and you drop it, its energy decreases. Okay, ari na, mamangkot pakotan. How will its energy decrease? By means of when you account for its energy content in terms of potential energy. So if it's elevated at a higher position, potential energy is higher. But once it's dropped, okay, it decreases. It lowers the energy content of the book because your potential energy is converted into kinetic energy. Dagdag siya mo. So there's velocity associated to it. So that's a process that is spontaneous. You drop something or allowing the potential energy of something to decrease, that's a continuous process as well. Now, if the process leads to a greater state of disorder, then the process is spontaneous. The state of disorder that is being referred to in here, class, is the disorder of molecules. Okay, particles, atomic particles in your material. So if the process leads to a greater state of disorder, then the process is spontaneous. So spontaneous processes, examples of which, these are theoretical examples. So by theory, a mixture of carbon tetrachloride and this particular 6-hexane, an organic compound, is less ordered than the two separate liquids. So if you're going to a mixture of carbon tetrachloride, meaning you mix already the two, carbon tetrachloride and hexane, its molecules is less ordered than the two separate liquids in terms of how orderly are the molecules of the resulting solution arrange themselves compared to the original molecules when they stand alone, like si carbon tetrachloride lang or si hexane lang. So therefore, we can say they spontaneously mix even though your delta H of solution is very close to 0. Now, in this case here, theoretically and in principle, it's just saying that whenever you mix two substances and the degree of disorderliness of the mixture is less compared to the degree of disorderliness of the, rather that there is less order in the, shall I say, the interaction of these two carbon tetrachloride and hexane substances compared to just the carbon tetrachloride and the hexane. So we say that it's a spontaneous process. Their mixing that is, their dissolution that is. So even though, as mentioned in here, that the delta H of this particular solution of these two is very close to zero, meaning gamay-gamay iya delta H of solution. So it's spontaneous, referring to the process of dissolution. So there are solutions that form by physical processes and those by chemical processes. So when we speak of physical processes lang of solution, I think this happens when we mix metals to form metal solution. There aren't any chemical reactions that are occurring in the process. So wala sa may chemical reaction nga natabo. Simple nagmix lang gid ang duwa ka metal. So that's a physical process. But when we speak of dissolution, one gets dissolved in another wherein the identity is totally different than the ones present before, then that is now what we call a chemical process of dissolution. Oftentimes, ang physical processes of solutions, formation of solutions is associated with gases and with metals. But with liquids, most of the time, there is a chemical reaction or a chemical process that accompanies it, the process of dissolution. Now, in the process of dissolution, your solute and your solvent interact to form the solution. This is in the process of dissolution, or one gets dissolved in another. The solute gets dissolved in the solvent. So you are forming what we call a solution. Now, in the case of crystallization, your solution, from your solution, you want to, shall I say, the term that is used when you go to unit operations later on, the term that is used is the solid precipitates out of the solution. If I will explain it in our language, it's just like halin sa imo, for example, may tubig ka kag kalamay, and you want to crystallize sugar that is in your water. So ang magwa, ang term na ginagamit from the original solution, your solid sugar precipitates out of the solution. Ang mabilin ang tubig na nagdissolve sa iya. So that's the process of crystallization. So these two are opposite processes because in here, in the dissolution, when you get to dissolve one over another, your product is a solution. In the case of crystallization, it's the other way around. You started with the solution, the homogeneous mixture, and from that, you produce your solute and your solvent. You separate the solute from the solvent in the process of solidifying it from the solution or precipitating it out from the solution where it is contained. Okay? Now, related to crystallization and dissolving solids in solution is the saturation condition. What is this? So crystallization and dissolution are in equilibrium. So if your solution is said to be in the saturation condition, or ang term nila ginahambal, it's a saturated solution already, it says here that crystallization and dissolution are in equilibrium. How do we simplify this phrase that during saturation condition, crystallization and dissolution are in equilibrium? Now, can anybody translate this in a much simpler manner that is easily grasped by, let's say, by first-year students like you, who are actually, compared then to our students, you are already third-year students. Ang ginatun-an yun na subo nga time kung old curriculum ka mo, gayon net ops na ka mo. Hindi mga amo ni. Now, if we will simplify this phrase, crystallization and dissolution are in equilibrium, can anybody simplify this? Crystallization and dissolution are in equilibrium. How do we restate this? That way it's easily grasped or understood. Anyone?
Same amount, miss.
Same amount of, sorry, nag-move kita. Same amount of what? What do you mean same amount? So, hindi na to siya pwede. What do you mean by this? Crystallization and dissolution are in equilibrium. That's the state of saturation. What do you mean by this one?
The amount of solution in both crystallization and dissolution are equal.
The amount of
Solution.
The amount of solution. We only have one solution. So where are you comparing it when you say it's equal? Can I ask Danielle? How do you understand this, Danielle? Crystallization and dissolution are in equilibrium when we have a condition of saturation. From the definition that we have here for dissolve, okay. Yes, miss. How would you simplify this phrase, Danielle? Crystallization and dissolution are in equilibrium in the state of saturation. What do you mean? If you simplify it, what's equilibrium in the first place? How would you view equilibrium? If you are to replace it with a different term, what is equilibrium?
Stable, miss, or
stable.
equal?
Stable or equal, or a state of balance, correct? Stable or equal, or in what you call a state of balance. So there are answers here. When the rates of condensation and evaporation becomes equal. We're not talking about condensation here and evaporation. We're talking about crystallization and dissolution. Although it's comparable in that sense to the process of condensation. No, it's not comparable because when we speak of condensation and evaporation, it's a totally different thing. But you use the term rates. This is good. This is a good term to use. The rates of condensation and evaporation becomes equal. When mixed, both solution, there will be no reaction occurring or it's balanced. Hindi matunaw ang crystallization sa solution unless heat will be applied. When maximum amount of solute is dissolved in a given amount of solvent under certain condition. This is how it's defined scientifically and theoretically. Okay. Right. This is when this is the definition of a saturation condition. When maximum amount of solute is dissolved in a given amount of solvent. Meaning wala na sa may ma-dissolve kay max na to siya, na max out na siya under certain condition. So if we will simplify this, crystallization and dissolution, isn't this that when we have dissolution, we form a solution? And in the crystallization, from the solution, we form solute and solvent. So I will use the term rate. So in the case of saturation, the rates of the solution and crystallization are equal. So when the rates of the dissolution and the crystallization are equal, so there won't be any crystals formed, or nor there will be any more dissolution that will happen. Why? Because the rates are equal. So that's the case of balance. That's a state of balance, or that's the case of being stable. It doesn't mean, so being stable or in equilibrium doesn't mean that these two processes of dissolution and crystallization stopped already. Wala na siya naguntat. Only that the rate of the solution, meaning the rate of the formation of the solution, is the same as the rate of the solution being processed in such a way that you will be forming separately the solute and the solvent. So since the two rates are being equal, there won't be any more solution that will be formed, nor there won't be any more solids that will precipitate out of your solution, because the two are said to be equal. So the key term there is rates. If the rates of dissolution and crystallization are equal, then we have a case of a saturation condition. As what is shared here in the chat box, if the rates of solubility and crystallization are the same, the solution is saturated, and we have reached what we call a dynamic equilibrium condition. Dynamic in the sense, class, nga wala naguntat. Sige na yung processes of dissolution and crystallization. Pero wala sang net formation sang solution kag crystals in the case of crystallization. Okay? Now, we've used the term solubility. Some of you use the term solubility in your answer in the chat box. So it's the amount of solute required to form a saturated solution. Or shall I say, that's the maximum amount of solute that a particular amount of given solvent can dissolve. When it has already reached that particular maximum amount of solute, then that is already, we say that is already the solubility of your solution. Since that is the solubility of your solution, we say that your solution is said to be already saturated. Now, saturated siya. Pero class, pwede na siya ma-supersaturated. You alter the condition. That way, your given amount of solvent can still dissolve an added amount of solute, even though it already reached the state of saturation. It's now what we call supersaturated condition. What is this? Your solution, the solution that was formed when more solute is dissolved than in the saturated solution. So if you have more solute dissolved in your given amount of solvent at saturation, then your solution is said to be at what we call the supersaturated condition. Okay? Supersaturation, meaning mas damo ang solute na na-dissolve at the saturation condition. How is this accomplished? We alter the environment. You alter the condition. Otherwise, hindi gina siya ma-dissolve. It can only dissolve, I'm referring to the solute, it can only dissolve the maximum. And that is at the same time the solubility of your given solution. Any question before I proceed with the next slide? So take note of these terms: saturation, solubility, and supersaturation or supersaturated. Now, let's go to factors affecting solubility. So what are the things that will be affecting the manner in which your solute gets dissolved in a given solvent? Okay, so we call that the solute-solvent interaction. So what are these factors? So number one, polar liquids tend to dissolve in polar solvents, or polar solids gets to dissolve in polar solvents. So like dissolves like. So that's number one. So miscible liquids, when are they said to be miscible? They are mixed in any proportions. So if a particular liquid gets to be mixed with another liquid in any proportion, miski bala ang isa damo, ang isa dutay, mix sila. Let's say you have A and B, liquid A and liquid B. Scenario 1, you have more of A and than B. Then you mix the two, and then they form a solution. That's one proportion. Another scenario is you have more of B than A. You mix the two, you still form a solution. So in any particular proportion, they still get to be mixed. So ang tawag na sa ila, miscible liquids. The proportion in which the two gets to be dissolved in another is not a factor that will affect whether it's going to be dissolved or not. Like Coca-Cola in water. Butay imo tubig, damo imo coke, ma-dissolve na nga duwa gyapon. Or you have more of coke, less of water, they still get to be dissolved. So we say the two are miscible. Now what about immiscible? So miski ano nga proportion, kung immiscible, immiscible gaya sila. Oil and water, for example, they are immiscible. They will never mix. So they're said to be immiscible. Now, associated with these factors affecting solubility is the intermolecular forces between your solute and your solvent. Now, in the case of water and ethanol, so water and ethanol are miscible because the broken hydrogen bonds in both pure liquids are re-established in the mixture. So meaning, we break the hydrogen bonds in water. We also break the hydrogen bonds in ethanol because ethanol is an organic substance which has OH in the original chain of the hydrocarbon. I think you learned that partly in your chem. So when this hydrogen gets to broken, dissociate from one another, when these two, water and ethanol, is mixed, gabalik lang man sila gyapon. So they are miscible because the hydrogen bonds in both of them, both in the pure liquids, are re-established. Nagbalik lang sila once the two gets already dissolved in another. I'm referring to water and ethanol. Now, in organic substances, the number of carbon atoms is something that we need to consider. So the number of carbon atoms in a chain affects solubility. The more carbon atoms, the less soluble in water. I think you have a background already of organic chemistry. So we have long chain carbons, we have short chain. So it says here that the long chain carbons will have less and less tendency to be dissolved in water than those that have less. How would you explain it? Why the more carbon, the less soluble in water? Anybody who can explain why the more carbons we have in our chain, the more or the less soluble your organic substances in water? Anybody who can explain this? We'll end with this, then we'll have a break. Anyone who can explain why damo carbon, less soluble in water? This is self-explanatory. You don't need any principle. Not that you don't need any principle, but you need you only need the basic and the most fundamental of principles in the solution. Why is it that the more carbons you have in your chain, the less it gets dissolved? Sorry. Why? You can write it on the chat box. Why, Gil? Let's say you will not ask Google over there. You just think, why do you think the more carbon atoms in a chain, the solubility decreases? The solubility of that thing decreases in water. Why? Hmm? Angelo? Why do you think Angelo? Why is it difficult to dissolve a long chain carbon molecule in water? Hmm? Oh, thankfully I have one here. Hydrocarbons are non-polar. But it says here the number of carbon atoms in a chain affects solubility. So it's not generally naturally said that whenever you have a hydrocarbon, it's already right away non-polar. The more carbon atoms, so you mean even if it has only 2 carbons, it will not anymore dissolve in water? Okay, I have here. More carbon means having more of a non-polar. Okay, we'll read it. More carbon means having more of a non-polar or hydrophobic characteristic. Since water is polar and like dissolves like, having more carbon lowers the solubility. Okay, another one. Bond between oxygen and carbon are not as polar like hydro and carbon. Okay, all of which are acceptable discussions, but hydrogen. Bond between hydrogen and carbon is more polar than carbon and oxygen. Bond between oxygen and carbon are not as polar like hydrogen and carbon. Kay kabudlay i-dissolve ang carbon atom is if damo ang atoms, dako man ang energy na need para ma-dissolve ang carbon atom. Not sure. Okay, I'd like to accept this definition, this discussion. Raw, it's raw, based on the understanding of your classmate, but not as scientifically researched as the others. Although, thank you for being resourceful. Even if you haven't really known, for example, that your hydrocarbon per se is non-polar, they will still have that tendency to dissolve in water. The more carbons you have, the more non-polar it is. And just like what Kessel is saying here, the damong imo carbon, you will need more energy to break those particular bonds existing between your carbon and hydrogen in your hydrocarbon. You need more energy. And the more energy that you need, the less soluble it is in water. But speaking of polarity, everything that was shared here is correct. So the more C and H bonds that you have there, the more non-polar is your hydrocarbon. Water as it is polar. So that would make it even more difficult for your hydrocarbon to get dissolved in your water. But let's say you don't know this particular principle yet, and you're just simply looking at the chain, the long chain and the short chain. You have this chain and you have this chain. Of course, a bigger chain would require bigger amount of energy without having to think of whether it's soluble or not, or whether it's polar or non-polar. Simply said that I have more carbon, I need more energy. So in terms of which of the two will have less likely tendency to get dissolved, that would be the one which has more bonds to dissociate. Damo siya sa iotdon mo. So kung damo siya iotdon, dako nga energy kinahanglan niya. Kumpara sa tong dutay lang, duwa lang kabilog, i-break down niya. So miski non-polar pa na siya, ina ang iya identity sang ila interaction sang carbon and hydrogen, there will be a tendency for it to still get dissolved. I shall say partly dissolved in water. Whereas if it's longer, hindi na gid siya mag-dissolve. Okay? Now, my time here is 2:35. We'll see each other at 2:45. We have a 10-minute break. Just, you don't need to leave the Zoom meeting. You may have your screen break. We'll see each other at 2:45. Okay? So, okay, I'll stop sharing here. So we're on factors affecting solubility, and we ended here with hydrocarbon chain, and in which you have more carbons in your chain. Okay, and it being less dissoluble or less soluble than the shorter chain. Now we go to solvent interaction in which you have already the presence of the OH group. Now in your organic chemistry in senior high, or a little backgrounder on this, what do you call these organic substances that have the OH groups? We call them what? They're very easy. We call them as, sorry class, we call them as, wait, why can't I see you? So there are two alcohols, correct. We call them alcohols. Let me share again, class. Okay, I was not able to see you. We call them alcohols. Okay, these substances that have the hydroxide group, or organic substances that have the hydroxide group. Now, the number of hydroxide groups in these alcohols within a molecule increases the solubility in water. So meaning, the more OH you see in your molecule, the more soluble it gets in water. Just like we use the generalization likes dissolves like. So the more polar bonds in the molecule, the better it dissolves in a polar solvent. And since this OH is polar in nature, then it gets dissolved easily in a polar solvent. The less polar the molecule, the less it's dissolving in a polar solvent, and the better, of course, that it gets dissolved in a non-polar solvent. Okay, so here's a table that would show to you the solubility of these alcohols. You have methanol, you have ethanol, propanol, butanol, methanol, hexanol, and heptanol. The solubility in water increases with more carbons present. Infinity meaning it doesn't get dissolved. Now, in terms of, shall I say, solubility in another organic substance, in this case, this is hexane. So methanol gets dissolved in hexane by this much. So we increase the carbon chain, it does not get dissolved already. Okay, so this is the solubility in comparison of these long chain alcohols, the short chain alcohol and this long chain alcohol with two solvents, water, which is polar, and of course hexane, which is non-polar as it is because we have carbon and hydrogen here. Okay, now we proceed. Now, network solids do not dissolve because the strong intermolecular forces in the solids are not re-established in any solution. So network solids, what are these network solids that do not dissolve because of strong intermolecular forces? Solids that don't get dissolved in water. Can you give me an example of a solid that don't get dissolved in water? Or their structure is referred to as network solids. Most of the time in class, these are composite solids, not just made up of one type of material, but several types of material. So one particular solid that does not get dissolved in water is, can you give me an example? There's a lot of solid. There are a lot of solids that don't get dissolved in water. We have, what solid does not dissolve in water? Network solids. Diamond. What else? Very good. Diamond. What else? Graphite. Very good. Silicon dioxide. Very good. These are network solids. What else? We have quartz. Okay. Hindi na panghatag niyo sa ako, mga stones, mga ano ba. Anyway, so these are network solids. They will never get dissolved in water. Even if you're going to place them in, let's say, alcohol or in an organic solution, it will not get dissolved because of the primary fact that they have very strong intermolecular forces. Okay, now pressure effects. This one is very easy to spot. This is really observable to us. This is really, shall I say, not so hard to observe. Solubility of a gas in a liquid is a function of the pressure of that same gas. Do you agree with this? How a gas dissolves in a given liquid is a function of the partial, specifically partial pressure of that gas in the liquid. Okay, we'll continue with an illustration here. So this one is at a lesser pressure. Your plunger here or your piston is at a higher position. We increase the pressure, the plunger is pushed down. So what happens? You get more gas dissolved in the liquid compared to this one, wherein your pressure is lesser. Okay, so that illustrates the statement that we just read a while ago. As we increase pressure, the more likely your gas will get dissolved in your liquid. Decreasing pressure decreases its solubility. It's in here. So the higher the pressure, the more molecules of the gas are close to the solvent, and the greater the chance of the gas molecule striking the surface and entering the solution. So we can conclude that the higher the pressure, the greater the solubility. The lower the pressure, the fewer molecules of the gas are close to the solvent and the lower the solubility. If you will proceed with CHE, you will have in your heat and mass transfer Henry's law, and it gives the solubility, or it calculates the solubility of a particular gas in solution as a function of the partial pressure of that particular gas. So this is the solubility of your gas, and K here is a constant. This is what we call as the Henry's law constant. I will not discuss this in detail because anyhow, you will learn this next year. No, not next year. Next year when you are in third year. And this P sub G is the partial pressure of the gas. So what you see here is Henry's law. The solubility of a gas as a function of its partial pressure. This one. If you look closely in the formula class, the greater is the partial pressure, the greater is the value of the solubility. Okay, anyway, this constant is a constant. It's taken from a table. We call it the Henry's law constant. Now, the reason why we have this spongy, biting, so refreshing when we drink Coca-Cola feeling is because these carbonated beverages have CO2 dissolved on them. So it's the CO2 that produces this biting. Kung wala na ya, sinong namian mag-inom sang Coke nga wala na CO2, nag-evaporate na do, nag-inom ka lang water nga butangan kalamay. So the thing that really gives it that taste, that signature taste, that Coca-Cola taste is the CO2. Now, once you release the cap of a bottle, you release the pressure on top of that solution of your syrup and water. May syrup kada kag water. So once you release the pressure, CO2 gets released as well. So less CO2, di na siya namit. Okay? As the bottle is open, the partial pressure of CO2 decreases and the solubility decreases. Therefore, bubbles of CO2 escape from the solution. It's not anymore good to drink. So that is why it's better to buy Coca-Cola in bottles, not in PET bottles, but glass bottles. We always buy in glass bottles. Unless we are in parties wherein, of course, hindi naman siya practical nga mabakal kagid sa botilya. So we buy in bottles, PET bottles. But the thing is, it's really contributing to the environment problem of plastics, right? The problem with glass is, of course, they are produced at high temperatures. Budlay mag-produce ang batos, glass kumpara mag-produce ang plastic. Plastic gina-blow lang na iya. Okay, but the thing is, the more and more plastic we produce, I don't know what will happen to the next generations. Will they have a world that we have experienced, and will they enjoy life the way we are enjoying it now? Okay. Now, what about temperature effect? So, ato pressure effect to siya. So, we release the pressure, we release the gas. The taste of the carbonated beverages will not be as good. Experience tells us that sugar dissolves better in warm water than in cold water. Example na lang, Milo or coffee, try to dissolve it in cold water and try to dissolve it in hot water. At elevated temperature, solubility is increased. Okay? So that's the reason why, aside from the fact na namin mag-inom sa coffee, a little bit hot, unless you are the one who likes iced coffee, or in the morning, especially in the morning, hot choco drink. When you drink cold, law ay imnon. Okay, so that's the reason why. Aside from the fact that it's difficult to dissolve in cold water. So that is why they have this stirrer to aid in the dissolution. Now, sometimes solubility decreases as temperature increases, but this is an exception class in the case of this particular compound, cesium sulfate. Okay, its solubility decreases with temperature, meaning we increase the temperature, mas hindi siya yan nag-dissolve. Unlike most solids that when we increase the temperature, we increase as well the solubility. So take note of that particular compound. That's an exception. Okay, now we proceed. So these are examples, class, of salts in water. Solubility of salts, grams of salt in 100 grams of water. So these are different salts. These are just examples, class. We increase the temperature. All of the salts that you are seeing here have curves that tend to move upward. So meaning we increase the solubility as we increase temperature. So the only substance here is this one, the one that I placed in the previous slide. Okay, its solubility decreases. So there's a decay here in the solubility. It goes down as we increase temperature. But the rest all exhibits increase in solubility as temperature increases. Okay. Experience tells us that carbonated beverages also go flat as they are warm. Hopefully, ma-face-to-face na kita. Hopefully, by the time you do your OJT, come third year, summer, you'll be able to go to industries, and one of those industries is the bottling plant. You can drink straight from the production line your cola drinks because they are really produced very cold, as if they came from the freezer. The purpose is for the carbon to get shall I say, dissolved intact in your bottled beverages when it's cold. So it's aiding more in the dissolution of your gas. When it gets warm, so aside from the fact, for example, that you open the cap of your bottled soft drink, CO2 escapes, wala na siya CO2, lain niya sa bore. Sino namian mag-inom ng soft drink kay init? Of course, you will have a very flat, shall I say, a flat taste. Nobody would dare to drink a particular drink which is lukewarm, or shall I say warm, or let's say at room temperature. So these carbonated beverages go flat as they get warm. So therefore, gases gets less soluble as temperature increases. In the case of pressure, in gases, we talk of gases, we increase the pressure, solubility increases. It's the other way around with temperature. We increase the temperature, solubility decreases. So naga-decrease if temperature is increased. Now, this same applies, this particular principle applies when we apply abating thermal pollution in bodies of water. Why is there a need to address the problem of, let's say, industries releasing their effluents into the bodies of water? Let's say, even if the effluents composition are within standards. What do I mean with this within standard class? Our effluents, the industrial effluents, when they are released into bodies of water as wastewater, they have to conform to as a set standards on the components that are present in the effluents. So if the composition of particular chemical substances, that most importantly the toxic ones, are not within the acceptable range, they should not be dispensed into bodies of water. First and foremost, they will kill right away the living organisms there because of their toxicity. Now here comes a case wherein that particular effluent, for example, adhere to standards, wala problema in terms of the concentration of the or the toxicity of such, there's no problem. However, when you dispense it to that particular body of water, it's very warm, it's very hot. So that's thermal pollution. And once we increase, so actually it's just, shall I say, local, shall I say, a local pollution, because it would be just in the vicinity where that effluent is discharged. So if there is an increase in the temperature in that part of your body of water, the CO2 that is needed by plant life and the O2 that is needed by animal life in that body of water is released. So wala siya gaka-dissolve, mas naga-escape siya sa body of water because of this increased temperature. And that is the reason why not only are industrial plants or facilities need to address the toxicity of their effluents, but also the temperature in which their effluents are discharged into bodies of water. Because if they are very hot, then there will be thermal pollution. And the CO2 and O2 that needs to remain in the water escapes. It gets, shall I say, it evaporates, it gets out of the water, it evaporates because of the increased temperature. So that is thermal pollution. This is very interesting when you go to your waste management pollution subject. I think come third year as well or fourth year. Okay, so here you learn the basics already. Now here are several gases. We have methane, very poisonous. Oxygen, carbon monoxide, poisonous also. Poisonous, makapatay na siya ya. For example, if you are, that's the reason why some that have, shall I say, difficulty in breathing, especially in very polluted areas, have this what you call attacks because of this carbon monoxide poisoning. And we have helium, all of which exhibits a decrease in solubility. Yeah? There is a decrease in solubility as temperature is increased. So it's relatively true for all gases that once temperature is increased, their solubility decreases. Okay, unlike pressure, if you increase pressure, solubility increases. Okay, now we go to the computation part. This is the part wherein we will end. I will continue discussing the colligative property parts on Tuesday before we go to a new topic, your last topic, which is thermochemistry. That is already the last. Now, the ways of expressing concentration here of solution, I'm sure you have, no, I'm not sure, by the way, I stand corrected. I'm not so sure if you have encountered this in your senior high, the way you express concentration of solution. So the most common and the easy way of expressing solution concentration is by means of mass percentage. Very easy in the sense that you need only to know the mass of the solute and you need it to divide by the mass of the entire solution. That's mass percentage. ppm, the parts per million. ppb is the parts per billion. But other than these simple ways of expressing concentration, we also have molarity, molality, normality. And as CH is, it's really very, very important that you know how to determine the molarity, the molality, or the normality of a given solution. Aside, of course, from knowing these three, which is very simple compared to the last that I have mentioned. So all methods involving quantifying amount of solute per amount of solvent or solution is a manner of expressing concentration of such solution. Okay, so solute, most of the time class, it's solute over solution. But there is one which is solute over solvent only. That is why you have here a parenthesis. So it could be amount of solute per amount of solvent or amount of solute over amount of solution. Generally, amounts or measures are masses. So these amounts that we're talking about here could be mass, moles, or volume unit, liters. So mass, moles, or liters. Qualitatively, solutions are either dilute or concentrated. What do we mean by this class? Qualitative meaning you are not required to give a number, or you're not required to give a quantity of that particular manner of expressing the concentration of a given solution. You're simply going to say dilute or concentrated. So when you speak of dilute, dutay lang da ang unod na solute. When we speak of concentrated, damo ang imo nga solute. That is why it's really very important, class, that quantitative manner of expressing solution concentration is done rather than qualitative, because what might be dilute to me is already concentrated to you. So it's just it's a relative way of telling that dilute has less solute and concentrated has more solute. But how less is less or how more is more is, of course, not as specific, scientific as when we quantify it with and represent it with a particular number. So quantitatively, we have percentage by mass, ppm, ppb. Molarity, molality, normality. Qualitative, we say dilute or concentrated. Now, the mass percent of a component in solution is the mass of that component, mass of component in solution divided by the total mass of solution, just like anything else. So if you want to know the percentage of a particular component compared to the entire mass of the mixture in which it belongs to, that's how we determine the percentage by mass of a component in solution. Okay, interrupt me if you think I'm too fast. Now, when we speak of parts per million, so the mass of a solution, the mass of a component in solution divided by the total mass of solution times 1 billion. As such, it says parts per million. What is the mass of that particular component in solution divided by the total mass of solution? Once you need to multiply it to 1 million because it's very, very small, then that's already parts per million. So actually, parts per million, class, kung kuaon mo na siya ang parts per million, you're just simply going to express it in terms of percentage by mass. The given amount in parts per million, you have to divide that by 1 million. That is already its percentage by mass when you multiply it by 100. Kung paon mo ni siya ang 1 million day, islan mo siya sa 100, that's the percentage of that particular component in your solution. The reason why it's multiplied, as I've said, 2 million, because this normally most of the time is very small. Now, in standards set by the government or agencies regarding toxicity or the presence of toxic substances in effluents, in wastewaters that are being discharged in bodies of water, they are always expressed in parts per million. So meaning, class, ang allowable lang nga amount is very, very small. That way, the living microorganisms, the living organisms in that body of water will not be harmed. So that is why it's expressed per parts per million. More so if it's parts per billion. So parts per million can be expressed as 1 milligram of solute per kilogram of solution. So your answer here, by the way, your answer here, which is having a unit of ppm, whatever is your number here, you just simply affix their ppm. The ppm unit class could be changed to milligram per kilogram. Okay, so let's say, for example, the answer here is 10 ppm. You just take away the ppm there. That could be equivalent to saying 10 milligram per kilogram, or that could be 10 grams per ml. Okay, that is also saying that it's parts per million. So 1 ppm is 1 milligram solute per liter of solution. Or shall I say, damo-damo na ho? ppm is equivalent to milligram per kilogram, milligram solute per kilogram of solution, gram per ml, or milligram per liter. All of this, 1, 2, 3, 4. 4 units meaning the same thing, representing the same thing. ppm, milligram per kilogram, gram per ml, milligram per liter. So they all mean the same. They are all equivalent. That's the ppm. For parts per billion, you just change this one class. Oh, the 10 raised to 6, you just change it to 10 raised to 9. Billion na siya. Meaning, gamay pagid na siya sa ppm. Kiti parts per billion na siya. Equivalent is 1 microgram solute per kilogram of solution. So if this is milligram here per kilo, this one is micro per kilo. That's your parts per billion. Actually, if you know this one, masunod naman lang ni siya. Kaya you just play along with the multiplier here. Okay? Now, before I proceed with the next 3, any question here regarding percentage, ppm, and ppb? You will, class, encounter this in your qualitative chemistry. You will have it second sem. And it's to give you already a backgrounder class. Not that ay nga gusto ta kamukulbaan ha. Pero importante, giniginatudlo ko sa inyo sa inyong qualitative chemistry. Quantitative chemistry na siyang tawag. Or we call it, in our time class, ang amon payatan when I was a student, it's 2 different courses. We have qualitative chem, we have quantitative chem. Now, in your case, it's merged into 1 course. Pila man ang diferensya sa edad ta. Miss Ali is already 50. You pila pa lang kamo. So, in your time now, it's merged into 1 course. 1 course which is called analytical chemistry. So now in your curriculum, it's your analytical chemistry. You will learn that in 2nd semester. And if I'm not mistaken, ang muna siyang pinakadako units yung subject. It has may dry lab na siya wherein you are required to really practice solving. You will love that because if you don't love that, you have learned to love that. Otherwise, you will bid goodbye to CHC already because this is vital, very important to us. Okay, concentrations. Even if you do already your feasibility study, you do already your thesis later on, you will not say goodbye to this because this will accompany you, this basic manner of expressing concentration. So that is why we have to change your curriculum. We did not change your curriculum, but the topics that are being delivered to you is different than your friends in ECE, your friends in CO-E, your friends in Math-E, because we see the need that this one is taught to you because we know that this is not given much importance when you were in your high school. So you need to know this. Otherwise, mga pangapagi ka mo pagkalabot yung 2nd sem and even in higher years because you don't know this. So I'm telling you this so that if you have any question, you will ask me. That way I can clear any misconceptions, or if there are things that you need to be fully clear, crystal, then you can tell me. Although I will give you exercises here for you to practice, that way you will know whether you know how to apply what we discussed this afternoon. Okay? So may pamangkot diri. Wala pamangkot. Okay, let me see. Okay pa ka mo? Okay pa ka mo? Isa na lang ang naga-thumbs up. Ang iban diin na natulog na. Sige. So ang iban wala gid reaction no. I see no reaction in 3 of my students. Ano ni kay Jose Miguel yung reaction man? Hi. If you're going to be a CHE, you should love challenge class. You should love this. If you don't like it now, you have to learn to love it. Otherwise, mabudlayan ka. No, I don't want, the reason why I want to teach chemistry because I want you, when you reach me later on, hindi gid ka mo laig ka mo rason, hindi ka mo kabalo. Kaya ako nagtudlo sa inyo. I made sure that you understand this. Because when you see each other again, when Doc Pandan in your second sem will see you again, she will really ask whether you know this. Hi? This is important. Stoichiometry na siya, analchem. Okay, anyway, sige. Wala question na. Atong na nagsiga ng iya mata sa kakapoy, ginawa yun na pamati. Bear with me. I will just finish this part then. We will continue the rest on Tuesday. Okay? Now, PPB, REC PPB, just like what I've said to you. It's the same rational expression here. Mass of component, mass of solute over mass of solution. When we talk about solution, times this time 1 billion because it's parts per billion. Okay? Mass of your component or the parts per billion of that component in your mixture. So how many parts of, let's say, ammonia is present in the wastewater that is being discharged into a body of water? Most of the time, that's parts per million, meaning gamay-gamay lang di dapat ang ammonia. That way, living things will survive in that body of water. Okay? Now, we go to mole fraction, molarity, and molality. Okay? We'll take this law para maintindihan. So we recall that mass can be converted to moles using the molar mass. Or ang pinakasimple nga term nga we associate with the molar mass would be the mass of the atoms as they are written in your periodic table. So if you have a compound, all you have to do is add all of those, and that would be the molar mass of your particular substance. Okay, the mass of one mole, and as such its unit is gram per mole. Okay, molar mass. So when you speak of mole fraction, I think this is explanatory. As engineers, you should know this. Fraction ng mansang sina nga particular component over the total moles of solution. So if we want to know how many moles of CO2 is present in our soda, then that would be moles of CO2 over total moles of your soda. What is the total moles of your soda? I'm referring to the soft drink. What is the total moles of your soda? No, moles of your syrup. Kung ano pa na dang sa syrup mo, moles of your water, moles of your CO2. All components should be added. All components of your soda mixture should be added. That should be in the denominator. And the moles of a particular component that you are interested in should be the only thing that you will be seeing in the numerator. And that's your mole fraction. Okay, mole fraction. Your answer here will come in the form of a decimal. So decimal siya. Now, when you speak of molarity, molarity, not molality. Molarity, that's the moles of your solution, solute, most of your solute over liters of your solution. So this time, class, you need the volume of your solution where your solute was dissolved. So you need the most of that solute divided by the liters of your solution. That is then the molarity of your solution. Most of the time, this is abbreviated. Let's say we say 10 molar NaOH. That means you have 10 mole of NaOH per liter of that particular solution. So to abbreviate rather mole per liter, we just write the capital letter M, meaning molarity ina siya. Okay, mole solute per liter of solution. That's molarity. The last one is actually do amulang ni siya the class ang kinalain sa tanan-tanan nga expressing solution concentration. Okay, most except this one has the denominator in terms of solution. Total mole solution, volume solution, something like that, or total mass solution. Ini siya ang iya denominator kilogram solvent. Kilogram plus gida, ang mass is kilogram. The numerator is the same with molarity. Same sa molarity nga mole solute. Pero ang denominator ya mass ang solvent but specified ang unit which is in kilogram. That's molality. Now, if you want to write the unit shorthand for molarity and molality, so you have capital M for molarity and small letter m rather for molality. So if you see an M, a small letter m, expressing solution concentration, that means mole solute per kilogram solvent ina, or that's the molality of your solution. If you wish to convert molarity to molality, or vice versa, you need the density. Everybody knows density, man. We're done with, actually, this was introduced in gases, but this is very basic, a basic quantity. Density is mass over volume. Okay? So when you speak of density, mass over volume of your solution. So mass of solution over volume of solution. That will be able to help you convert from molarity to molality. Let's see. Okay? I will annotate here dire lang para hindi na ta mag-silo. Now, let's see. You have molarity. So molarity, we'd like to convert to molality. So what you do, unit of molarity, I'll place it here, is moles solute per liter solution. Now, if I will use density class, ang density is gram per liter, right? Gram per liter. So then it must be multiplied here suli. Dapat ang liter ari sa babaw, ang grams ari sa dalom. Okay, grams per liter mass over volume. So then it would be 1 over the density. I'll get the unit here. This is in grams solution. Mass of solution over liter solution. Okay. Now I'm able to convert. Take nota. I'm able to convert. You have now mole solute per gram solution. Okay, per gram solution. That is your resulting set of units when you divide your molarity by the density. This is the density. Now remember, I would like to know, I will be converting my molarity to molality. So paano siya ma-convert? This is gram solution per moles of solute. What will I do? Paano ko na ni siya dayon na convert B to N? Okay, this is mole solute per gram of solution. Ari siya klasong mole of solute per kilogram of solvent. So what do we do? Abe, anybody? Oh, somebody is writing on the chat box. Using mass percentage, miss. Okay, how will I use mass percentage? Will it be used straight here? John, to the one who suggested this one. Let me see. You have already more solute per gram of solution. Now, if you're going to use mass percentage, how will you use it here? I will share the Jamboard ha para makita sang tanan. Anyway, this is the last thing that we're going to discuss. Wait, I don't see my Jamboard. Wait ha, para diretsyo ang pag-solve ta. We'll close this for now. Wait. Jamboard. Where's my Jamboard? I'll stop sharing for now. I'd like to see my Jamboard class. Wait, here it is. Sige. I'll share it to you. Share Jamboard. Okay, we were saying, I will start from scratch. That way it's clear. I will have to convert molarity to molality. This one is moles solute per liter of solution. Okay, this one is moles solute per kilogram solvent. Okay, a while ago, I'd like to use a different color. Like a while ago, we started with the unit for molarity. So I have moles solute per liter of solution. Okay, now, okay, somebody wrote in the chat box. Okay, sige, we'll see. Now you have to divide this by the density, which is liter of solution. And this is gram. Or by the way, when you use liter of solution, your density class will be kilogram per liter. Because if it's grams, that would be per ml. Okay, so this is kilogram solution. Okay, there's a different font here so you will know what I'm trying to write. This is your molarity. This is your density. So what happened between the two is, I'll just cancel the liter of solution. I have converted the original set units of mole solute to kilogram of solution. Now, remember, your goal is this. This is your goal. You will have a unit of mole solute per kilogram solvent only. Now, what will you do? What will you do? I'll read the suggestion of John Mark. Mass percentage of solvent means to convert grams of solution to grams of solvent. Do you get this? Mass percentage of solvent to convert grams of solution to grams of solvent. Multiply to kilogram solution divided by kilogram of solvent. Very good, Mark. Do you understand this, class? I'll write it here so you will understand better. So you have now your molarity and you have your density. I want the denominator to be kilogram solvent. I don't have any problem here. It's already more solute. If my goal is more solute per kilogram solvent, I need to multiply this or I need to divide this with something. What is that something? I will divide it by, so remember, I want to get rid of kilogram of solution. So I'll place here kilogram of solution to kilogram of solvent. Why would you do that, Miss Ali? I'll change my font. That way, I get rid of the kilogram solution and kilogram solution here. I'm left with mole solute per kilogram of solvent. But the question is, if this is molarity and this is density, this is actually 1 over density, what is this? This is kilogram solute over kilogram solvent, rather kilogram solution per kilogram of solvent is what? 1 over percentage solvent. Percentage solvent, specifically percentage by mass of solvent in your solution. Isn't this percentage of solvent, mass percentage of solvent in solution? We just use division, that way we can cancel this one. Just like the way we did here, we use division by density. In here, we use division by percentage mass solvent. Do you get it? So the goal, class, is you end up with the desired unit. These are your desired unit. Mole solute per kilogram solvent. The process that we did here, this is the usual process my student would work on, especially if they do not know the solution to the problem. They do what we call dimensional analysis. You work your way through your unknown, or you find the unknown using or manipulating the units of the quantities that are known to you or that is provided in the problem. This comes very handy, class, especially if when you are given a problem, hindi ka kabalo kung ano ang iya formula mag-solve. Hindi ka kabalo sang formula mag-solve, inaobra na sang estudyante, premi is dimensional analysis. I'll manipulate my units that will end up with the unit that I want.